Oh, really? All right, let's start with what you know. Okay? Average rate of change. We talked about that a lot in pre-cal, right? Average rate of change. Tell me what average rate of change is. You've already said it. Slope. This is nothing more than a fancy way to say slope. And in fact, I'm going to show you some really fancy ways to do it that are going to help us do the calculus. Welcome back. Right in time for Aroc. That's what they said they have to wait till all the new ones are given out before you can sign your own stuff. Oh, good Lord. So that's it. I turned my No, they didn't give Thomas his. Oh my God. They didn't even take your $10, did they? They didn't even take your $10, did they? Look at that. All right, so tell me how we find slope or Aroc. It's okay, so when we do Aroc, we did y2 minus y1 over x2 minus x1, or we did change in y. Do y'all remember whenever I addressed it that way? Change that delta. Change in y over change in x. Yes, I remember that. This is gonna feel like I'm overly complicating this. Maybe I should wait on that and just do that. Let's practice. First, let's practice an Aroc problem, and then I'm gonna show you kind of the more complicated that we're gonna use to do difference questions soon. And let's do this. Okay, so let's say a rock, I'm gonna just read the first example that's in here. A rock breaks loose from the top of a tall cliff. Oh, okay. What is its average velocity during the first 2 seconds of its fall? First 2 seconds. So you need a little equation here, and I'm just going to give it to you because this is, have y'all taken physics or you're taking physics now? Or, okay. When objects fall from rest, we say that they fall at 16 t squared. T is your time in seconds. This is going to tell me how many feet it falls over so many seconds. So if I want to know the average over the first 2 seconds, I'm going to find where it is at second 0, and then I'm going to find where it is at second 2, and I'm just going to find the slope between the two, because it's going to give me an average rate of change, right? Because that's what slope does. Does that make sense to everybody? So the Aroc for this one, I'm going on the interval from 0 to 2. Yes? So I'm going to find its position at time 0. Does that make sense if I write it that way? Y of 0. And I'm going to find its position at time 2. And I'm writing it this way for a specific reason, and I'll show you in a minute. So here I'm plugging in. So 16 times 0 is, of course, 0. And here I've got 16 times 2 squared, which is 64. Everybody okay there so far? All right. So if I want to know the, okay. Here, in this case, the velocity, because velocity would be feet per second, and since I'm doing a rate of change in how because this would be at 0 feet, this would be at 64 feet. So if I find the slope of that, it would be feet per second. Yeah. It's always a rate. I'm always looking at that rate. Okay. So to find this rate of change, I'm going to do 0 minus 64 over 2 minus 0, or vice versa. It doesn't matter which one, as long as if you start with this one, you start with this one on the bottom, right? And so I find that it is actually, what? 32? 32 negative. Why is it negative? Because it's falling, right? So it's negative 32 feet per second. So I show you all that because that's an easy example of the velocity back, what we did in pre-cal. But I want to give you another way to write the Aroc formula. Okay, so we said Aroc is slope, which is, we said y2 or y1. We'll say delta y over delta x. That's a little bit easier, more concise way to do it. But I could also say, and I don't want you to get confused whenever I put this on here. I could say y of some time, right? Minus, and then I've got to get from here to here, right? Okay, let me see this well. Start over. If this is y of t, my change in x here, what? I start at the time, and I'm going to add some change in that time to it. So in other words, the distance it spans, instead of addressing this as change in y, I'm going to address it as change in time. And I'm going to add, listen, this looks really crazy. I know it does, but it'll be okay. I promise. I promise it's going to all come together. So instead of writing this equation as change in y over change in x, I could write this equation as y of, this would be my y2, right? Y of t plus change in t minus y of t over the change in the time. That's if I subtracted the x's there. It looks funky. I know it looks funky. No, yeah, do the other, but I want you, whenever I throw this at you here in the next day or two, it'll help to see where it comes from. So really, this is, if it wasn't y and it was f, right? And I said, I don't want to call it delta t, that just confuses me too much. I'm going to call it h, and I'm going to say h represents the change, the difference in the time here. So I'm going to say f of t plus h, so that it works for any equation, to find the average rate of change for any equation, minus f of t divided by h. I've just made something that's super duper easy, and I have way overcomplicated it, right? But there's a reason for that, and we're going to get to it. All right, but do you understand? You're not going to remember this right now, and that's okay, but do you understand where it's coming from? You understand that? Okay, so put a pin in that. We're going to come back to that. The thing here, this is average rate of change, right? That means I'm going over a time period, right, between 0 and 2. I can find how it changed, but what if I wanted to know at 1 second how fast is the rock going? How are you getting 32? At what you're finding the average rate of change from 0 to 1. But if I want to know the instant at 1 second, like if I could just pause time right then at 1 second and see how fast it was going at that second, because is it going at a constant speed? It's falling, right? So at every moment it's changing its speed, right? It's not. Oh my gosh. The point that I am getting to here is that I can't find an instantaneous time. What I could do is, my goal here is I want to make this as small as possible, right? I want the distance between them. Like if I wanted to know at second 1, so here's this rock, he's falling down this cliff, or he's being thrown off the cliff, whatever. Thomas threw a rock because he was ticked off about something, and After 1 second, how fast was the rock going, right? I want to know when my rock is sitting right here, how fast he's going. Well, I only know how to find the speed between two times, not at one specific time. But if I could use this to think about, okay, from here to here, I could find the average speed, right? What if I could shrink that distance in? So what if I could go maybe, like I asked you one and you said between 0 and 1, okay? So if I wanted at time 1, what's the rate of change? Maybe I went between 0 and 2 to try to find it. But what if I could really shrink that area in? What if I could go from 1/2 to 3/2, and then I could shrink it even more so that I'm doing average rate of change from, I don't know, what's even closer, 0.1 to 1.1. But you see what I'm saying? What I am decreasing, I am trying my very best to get this as close to 0 as I can. But I can't make it 0. Why? You can't divide by 0. You can't divide by 0, right? So for instantaneous, which we call Aroc, instantaneous. Did we talk about Iroc at all? Okay. Which is Iroc. My goal is for H, which remember H was the change in time or the change in X or the change whatever. My goal is to make that be as close to 0 as I can get. So my goal is to make H 0 or as close as I can get. So this is where limits come in. So what we're going to do is we're going to plug in these numbers for this change that get really, really, really close to 0, but they're not quite 0 yet. And we're going to see if I approach a number. Okay, y'all ready? Let's take this same example. So we're still 16 t squared, okay? Thomas threw his rock. I want to know how fast the rock was going. So I'm looking for velocity at time 2. I can find average. I can look at the average. I can find how fast, right? I can find where it was at 0. I can find where it was at 2. I can do average rate of change and have the feet per second. But what if I wanted the instant it's 2, right at 2? So I want to think about that formula that we talked about, the change in y over the change in x. And I'm going to use that one that had that h in it, right? Because that's the one that gives me the time. What did h represent again? The change in time. That's exactly right. Look at you go. So I'm going to do y of t plus h, which is that change in time, right? Minus y of t over h. But this time I'm going to use, and this is going to, I'm trying to find my Iroc, remembers what I'm doing. I'm going to plug in 2 for my time. Okay? All right. So I get y of 2 plus h minus y of 2 over h. Is anybody completely in the dark right now? You see that this is a little bit? You will. This is nothing more than the slope formula. I just overcomplicated it because I'm trying to get these zeros in here. I'm trying to get this to go to 0, okay? But I can't divide by 0. But this is just an overcomplicated slope. That's all it is. It's still a rate of change. Okay. So now, my question is, what is y of 2 plus h? Well, I have an equation for y, right? What's the equation for y? 16t squared. So it's 16t squared. Well, this is algebra, right? I can FOIL that out. T is where I'm looking for that instantaneous change. Okay, so if I'm looking for where is it, so I'm leaving the h in here. because my goal is to get that to 0, but before I can get it to 0, I'm going to try to work this because I can't just throw a 0 in the bottom. It just doesn't work like that, right? All right, so I'm just going to see what happens. I'm going to see what happens here. All right, so 16, 2 plus h, 2 plus h. Oops. So that'd be what, 4 plus 4h plus h squared. What things? What's 16 times 4?
Can I have your attention, please? Students with the numbers 181 through 240, please report to the lecture hall to pick up your devices. Thank you.
What am I what? Yeah. You're talking about because it's not in standard form? I'll put it whenever I come over here. That was just the way it was. I don't know. Okay, so I've got, I'll put it like this for you, Jason. 16h squared plus 64h plus 64. That is this piece, yes? Everybody's okay with where that came from? Minus, well, now my question is, bless you, what is y of 2? That should be a lot easier. Only one of these is hard, and it's always the first one. What's y of 2? 16 times 2 squared, 64. So minus 64 over h. So the 64's cancel. That's exactly right. And now look what's going on. What has happened? Can I clean it up anymore? Probably. What do you notice it has? H. There's an H in everything, right? And 16, but that's not the bottom two. I'm not, oh my gosh. I'm gonna, as long as you can take one out of everybody, you're okay, because I'm adding up top, right? And so it's kind of like doing this, h times 16h plus 64 over h, and the h cancels. So I took one away from everybody. So now I have 16h plus 64. What was our goal? What were we trying to do in the beginning? What close to 0? And essentially, if we could plug in a 0, that would be ideal, right? Because that would mean there's no distance between. Remember, h is the distance between. I'm doing average. So if I could get that to 0, well, can I put 0 now? Yes, I can put 0 now. How? Why can I put 0 now and I couldn't before? I'm not dividing. There's nothing in the denominator anymore. So now I can say, well, you know what? At time 2, and this only works at time 2, because remember I plugged in 2 plus h and y of 2. At time 2, put a 0 in for h. So at 2 seconds, my velocity would be 16 times 0 plus 64, which is 64. Units are very important here. You lose points if you don't put units, so make sure. 64 feet per second. Yeah, you do. Technically, it's negative 16t squared, but. So what we did was we found the instantaneous velocity at time 2. So we haven't known how to do that before. So it's kind of like this. I can do whatever it is I'm looking at, right? I can do the slope between these two. And what's going to happen is, it's okay. This is, yeah.
We said these two, and then we saw this side. But shouldn't this answer equal this? No.
Say that again.
So we put these together at the beginning of the equation, and then we solved this side. So like, where does this side come in from?
This was not, this, we just, here, we just found this part. Yes, and then we found this part, because you're doing this equation, right?
Yeah.
So this part of this equation is this. which is the 64. Y of 2, I think you just didn't write it down. So yeah, Y of 2 is 64. And then it's still over the H. And the 64s cancel, and then that's where.
So we were just looking for the H.
Yeah, we were looking to plug in H. The whole goal is to get H to be able to put a 0 in for H.
Okay.
That's the whole goal.
Okay.
Let's do this. Let's do this. Let's take. We are. Same equation. Rex drops his rock off the side of the cliff. Oh my gosh. I didn't even hear what you said, but I'm sure it was ridiculous. Okay. No, what did he say?
I did not. You literally heard me. I didn't say nothing. I literally said shut up. I said shut up.
Okay. I want to know what is the average velocity the first 3 seconds, and then I want to know what the instantaneous. Let me make sure I ask it the same way they're going. Let's find the actual velocity or the instantaneous velocity at oh dear. What's the difference in the two questions? Aroc and Iroc. But I'm essentially using the same equation, right? It's just that I'm looking at that change. I'm looking to make that change 0. So for this first one, that's just a what formula? A slope formula, right? We did a lot of Aroc in pre-cal. If it's the first 3 seconds, that means I need from 0 to 3, right? Well, okay, I can do that. At 0, it's 0, and at 3, it's, what's 9 times 16? What is it, 144? I mean, I believe you. Yes. Okay. Okay, so the average rate of change over the first 3 seconds. Remember, I need to do the correct units. So I'm going to do 144 minus 0 over 3 minus 0. Yes? Everybody sees where that's coming from. Which is, I don't know, 3 goes into there how many times? 4v8 feet per second. So that means over the span of that time, maybe it starts out going 100 feet per second and slows down to 20 feet per second, but on an average, it's going that fast, right? I'm really exaggerating the numbers here. It's not going to go that fast. But over the course of that time, it averages for you. On your way to Columbia, right? You're not going 50 miles an hour all the time because the speed limit's 30 in Camden, but it's 70 on the interstate, but then you get off and it's 45. But maybe over the course of 30 minutes, you average 50 miles an hour. You see the difference in the average? But if I said, at the exact moment that you're on I-20 at the Elgin exit, what's your rate of speed there, then maybe you're going 75 miles an hour then. It could be vastly different is what I'm saying. You understand the difference in the two? Okay, so this is how fast the rock is going. This is the average speed of the rock, right? It's averaging 48 feet per second. But now I'm saying at 1.5 seconds, how fast is it going? At that exact moment, how fast is that rock going? That's just slow. Yes. You're using that equation. It's still the slope equation, but the difference is I've got that change, that H in there, and that comes from, because I'm trying to get I'm trying, instead of averaging from 0 to 3 like I did, right? Here's my rock falling, and I went from 0 to 3 and I averaged that together. I'm trying to smush that in so that I'm getting as small as possible in the difference of the speed, and I want this to be at 1.5, and I want to know what's the speed there, not where it is, but how fast, right? And to find a rate, the only way I know to do rate is slope. So I'm using that slope equation, but adjusting it so I can do here. Yes, yes. Yes. So if you want to, in general, stop trying to overcomplicate it, Miss McGee, and just give me like the formula kind of thing. Gina's right. If I want Iroc, I'm Aroc, I'm slope. That's just my normal old plain old slope. If I'm doing Iroc though, I want to know time. This is where I am doing f of t or x or whatever it is plus h minus f of x over h. Okay, this is Iroc. That's Aroc. Essentially, though, they're the same thing, really. But this just allows me to manipulate it a little bit so that I can put a 0 in for h. Remember, that's my goal. My goal here is to let h be 0. Yes, yes. So if I want it at 1.5, right, I need to say, okay, f of 1.5 plus x, plus h, sorry, minus f of 1.5 over h. Okay, and this is where I kind of came off to the side to work the algebra of it so I didn't lose myself in the problem. What is f of 1.5 plus h? What is f of 1.5? So f of 1.5 plus h, oh, it's nasty outside. 16 times 1.5 plus h squared, gross, right? What is this, 22.5, 20, what's 15 squared? 225, 2.25. 2.25 plus 3h plus h squared. Is that what y'all got? 16 times 2 1/4 would be 32 plus 4, 36. 36 plus 16 times 3, 48. You will not have to do this kind of stuff in your head. I'm just, look at the storm, y'all.
Can I have your attention, please? Students with the numbers 241 to 301, please report to the lecture hall to get your devices. Thank you.
All right, now I'm going to do f of 1.5 so that I can plug this into my equation. So I get 1.5 squared is 2.25, so 16 times 2.25. We've already done that one time. 32 and then 1/4 will be 436. I hope you're starting to see a little bit of a pattern here with how these numbers are kind of canceling each other out. Yes. So this is going to be this one, so 36 plus 48h plus 16h squared minus 36 over h. Yeah, yeah. So, yes, yes. The h's are going to cancel. You're going to be able to take an h out of everything. And if you've done this correctly, what's going to happen is you're not going to have a fraction anymore with the h in the bottom. And you're going to be in a scenario where you can make your goal happen. You can put a 0 in for H, and you can have, so I've got 48 plus 16H. So how fast, at 1.5 seconds, how fast is that rock going? 48 feet per second. Oh, that's ironic. Yeah. You're throwing it up. Yeah, he is. No. Right. That's actually a theorem we're going to learn, because even though this one, Aroc equaled Iroc, is that what we said? Yeah. There is a theorem that we learned that if it's a continuous function, I mean, we're jumping way ahead here, but if it's a continuous function, there exists at least one time where Aroc has to equal Iroc, at least once over the span of the time. And that makes sense, because if you're averaging 55 miles an hour, yes, you have to, at some point, you have to hit 55 over your span of time. Right. Wasn't that cool? I think that's cool. Okay. No. Limits. We're just going to intro limits. We're not going to do a lot of them. It'll be okay. This is okay. I should not have told y'all that, because y'all are going to be saying that every day. All right. So limits. Here's what limits mean. You know how I was talking about we want to plug in 0, but it's hard to plug in 0 because we're dividing by 0. We can't divide by 0. And if I could get that distance to be 0, which you really can't do because that's not really possible to make a distance between 2.0, if you could make it 0, then essentially that would solve my problem, right? Well, that's where a limit comes in. That's what a limit means. A limit means if I get as close to that 0 as I can, right? Maybe I'm 0.0000001 and 0.00000 with one extra 0, 1, whatever, and I'm between those, and I can make it, I could just decrease that distance between as much. That's where limits come in. Now, limits are not always that difficult to understand. And so, did I show y'all limit notation before? I feel like I did with in behavior and pre-cal. Did I not? No? Okay. So here's the way I write it. I do a limit. This is literally like you did limits, you just don't realize you did limits. The limit, and then under it we do as x approaches, and here's where I do some value. I'll either do a number, I can do an infinity, I can do a negative infinity, I can do whatever. So the limit as, let's say x approaches 0 of, we'll just do something easy like just a little polynomial, x squared plus 3x. Well, we all know this is just a parabola, right? It looks like this. So this is saying as x gets closer and closer to 0, what does this become? Well, it's just a value there, right? As I come into 0, wherever it may be, should be at 0, 0. As I come in from the left, and as I come in from the right, as I get closer and closer to 0, what's my y value there? But what's the y value? 0. So the limit as I approach 0 here is just 0. I'm looking for the y value is what I'm doing. Okay? Now, it's y value. Now, if it's defined, okay, if it is a continuous function and it is defined right there, it is just the function value. So my method 1 of evaluating a limit is just to plug it in. So always try to plug in. So in this case, if I plug 0 in for x, I get 0, and that's right? But what happens when I can't plug in? So maybe I ask you for the limit as x approaches 1 of this. What in the world is going on here? Think back to pre-cal when we did rational functions. What you got? You say that, what's that? Okay, so you're saying the one that does something like this? Does anybody disagree? I disagree. Several things happening here, right? One, what happens? I'm trying to go to 1, so if I plug in, what happens? It's 0 on the bottom. If you want to kill a kitten. That's right. That's exactly right. My problem lies in that if I plug 1 in, I get a 0 in the bottom and I can't have that. So problem, so I can't do this to evaluate that limit. So let's think about what it looks like on a graph. What's happening at 1 on the graph? There's one of two things, if it's not defined, that are happening. It's either an asymptote or a hole. How do I tell the difference? That's exactly right. If it cancels out top and bottom, it's a hole. If the bottom to 0, it's an asymptote, right?
With the numbers 302 to 362, please report to lecture hall to state your devices. Thank you.
It's a difference of squares. What's happening at 1? There's a hole, which means if I were to graph this, it looks like this. There's a hole at 1. Remember how we were doing that manipulating with that other equation where we were getting the h out of the bottom so that we could plug in what we needed to? We've just done the same thing with this one. We've manipulated it so that look what happens. Can I evaluate it now? Yes. If you plug in 1, what do you get? 2. So even if the function has a hole, it still has a limit. There's still a limit there. And here is why. As I come in, look what this graph is getting closer to. As I come in from the left, the y is getting closer and closer to what? What's that y value? 2. If I come in this way, so I'm approaching when x is 1, and as I do that, y is getting closer and closer to 2. I think I'm going to save properties of limits for tomorrow and run you through all of these tomorrow. I think I will stop there because some of y'all are glazed over on me. Take out the packet that I gave you. Yeah, it's just all homework. We're going to go 1 through 20. All of these are substitution until you get to 15. So on 15, here's what I want you to do. You see that table that's up there? Everybody see the table that's there? Oh, never do the quick review ones. It always starts on the section 1-1 exercises. Yeah. No, don't do those. Yeah. Yeah, do 1 through 20, but don't do 1 through 10 at the top. Yeah. Never do those. All right, so look at 15, because I want to just walk you through this real quick, because this is kind of the other way to look at and we'll really dig into limits tomorrow. This asks you, if you look in the beginning, it says, what's the limit as x approaches 0 of f of x? right? And it asks you for a table. I don't want you to do the table unless you have to do the table. In other words, if you try to plug in and you can't, then use the table. So 15, can I plug in 0 for 15? Yes, because there's no 0 on the bottom, right? Look at 16. Can I plug in 0 for 16? Why? There's a 0 on the bottom. So what can I do? I don't really like the table format because I feel like it's, when you get to 17 and 18, you're going to have to put those in your calculator and do the table. But for 15 and 16, you can do some algebraic manipulation on 16, right? Find the whole and then plug in. Do you see what I'm saying? Or use the table. Use the table. Stop at 15. Stop at 15. Do 1 through 15. Do 1 through 15. We'll hit that tomorrow.